Okay. Played basketball this morning, man. Not in very good shape. It hurt. Need to start riding my bike. Let's see. Only us so far. We'll wait a few minutes to see if anybody else shows up. Doesn't Nebraska Land Day start or something this week? Some kind of event?
Yeah, I think the radio is this weekend.
Should be more people kicking around town.
Right.
I've lived in, I think, 3 towns. I've lived for more than like 25 years in towns that have rodeos, and I've never been to a rodeo. I lived in from 1979 until 1980 until 1992. I lived in Livermore, California, that has a big rodeo. Their biggest event of the year is the rodeo parade. Well, it used to be when I was there. When I was there, it was kind of a hick town. Now it's like a winery town, full of rich people, like Steph Curry. Steph Curry lives there, and he's so all these rich people in fancy restaurants now. No more. It's not so much rodeo centered. But yeah, of course, I've lived in North Platte since 2007. No, man, come on. Let's see, is anybody gonna connect with us today? Maybe I should try to connect to the room. Room system. 7, 2, 8, see if anybody's there, wherever they're going to. Valentine? Or is it Imperial? I don't know if nobody's there. Okay, well, we'll go ahead and get started, I guess. Let's see, where were we at? Drag forces, we didn't do that yet. Drag forces, well, we did do drag forces a little bit, but not too much. Elasticity, stress and strain. So friction, let's do a little review of friction. Let's go back to section 5.1. Talk about friction a little bit. Friction, remember, is this force between two objects because of contact of surface, right? It's because of roughness of surface. And there's 2 kinds of friction. The type of friction that is present when it's not moving. So if you try to push against something and it won't move, that's because of the static frictional force, right? But once you do get it moving, once you push hard enough to actually get it moving, Turns out it's a little easier to push most of the time. And the friction that resists your pushing, because it still is hard to push, that friction is called kinetic friction. And they're both using the same equation or the same formula to calculate what we're doing here. But one of them has an equal sign, kinetic friction. It's always the same number, no matter how fast you're moving for the most part. Whereas static friction changes depending on how hard you push on it, right? If you push on it and it doesn't move, if you're pushing with 5 newtons, then the friction will push back with 5 newtons if it has enough friction to do that. If you push on it with 10 newtons and it still has, and you're still less than its maximum, so in other words, with this formula, what you're calculating is the maximum amount of friction it can exert, or the maximum amount of friction there can be if something tries to push on it. It's not always there unless you push on it. If you push on it, then it pushes back with some friction. But there's a maximum amount, and once you get over that maximum amount, then it switches over to kinetic friction and slides along. And of course, you have to know this coefficient, or you have to calculate it. In this case, we give you a bunch of different ones for different pairs of materials. But you can also calculate the kinetic coefficient of friction. Let's say that they tell us they're on a flat surface. When you're on a flat surface, you know that the normal force and the weight are equal to each other as long as there's no other pushing going on in that direction. So if there are no other forces in the y direction, and you're on a flat surface, then you know that the normal force and the weight force have to counteract each other and they have to be equal. So if you know the weight, you know the normal force. And if they tell you the frictional force, if they tell how much force and friction there is, then you can calculate mu, which by solving this equation simply. There are other situations where you may be able to solve for mu as well. That's basically it. So that's friction. And here we did an example. The first example that we did right away was one that's not on a flat surface because it illustrates why the normal force is so important. If you're on a slope, like a skier, then the normal force is pointing this way and the weight is pointing this way. And forces that aren't pointing along the same line cannot cancel each other out. So only part of the weight cancels out the normal force, and you still have a little bit of the weight left over, the part that points down parallel to the slope. And that's what makes the skier slide down this way. If they have enough of this weight force left over, and it's more than the frictional force pushing backward as they are trying to slide down the hill, then they'll slide down. How many of you have been? Well, you guys haven't been skiing, right? I forgot. So if you ever go skiing, the first thing you'll do is you go on a bunny slope, which the little hill at the park here in town, what's Cody Park? That little hill that everybody goes sledding on. That's the size of the bunny hill at the ski slopes, where you learn how to ski. And you kind of have to push yourself off and kind of push your skis down. And the reason that they do that is because they want to have a lot of friction here and not very much of this weight force pulling you down so that you don't go too fast while you're learning how to ski. The bunny slopes. So that is very similar to drag forces, except in drag forces we're not just talking about two surfaces, rubbing together in kind of this two-dimensional plane thing. In drag forces, we're talking about something moving through something else. So like a submarine moving through water, or a car moving through air, or an airplane moving through air, or whatever. In this case, it behaves a little bit differently. The friction behaves a little differently. We call it drag instead of friction. In the case of drag, you have to account for how much cross-sectional area is pushing against the fluid. So if it's a submarine, you have the kind of this circular area that pushes against the fluid at the nose of the submarine. If it's a car, then it's kind of this rectangular area. If it's a person, then it's kind of this rectangle with these sticks and the little round thing on top, right? You have to know kind of the area that is pushing against the fluid. And in the end, what you really need to know is how much area. And that's what this A is. The A tells you how much area is pushing against the fluid, perpendicular to the fluid, the cross-sectional area, essentially. And then you have rho, which is the density of the fluid. So that's how much mass the fluid has per meter cubed. And then you have the v squared, which is the velocity of the person, and that's very different than the friction. In the friction, it didn't matter how fast something was going. In this one, it does. In this one, the faster you go, the more drag you get. And there's a real good reason for that. It has to do with what we call turbulence. Turbulence creates more drag, and the faster you go, the more turbulence you create. We'll learn a little bit more about that later. And then you have this 1/2 out in front, which comes from calculus. And then we have this C, which is the coefficient of drag, or the drag coefficient. And that is dependent on a few different things, like the fluid, and there's other things. But so that's different for different reasons. But essentially, what it comes down to is that it's related. It's directly related to the velocity squared. So the faster you go, the more drag affects you. So it becomes very important for things that go fast to worry about drag. So this is a great picture of a bobsled from above. And this isn't even a very modern bobsled. Actually, this is a one-piece bobsled. Now the bobsleds often have two pieces, so the bobsled actually rotates in the middle a little bit. Kind of interesting. But here's an airplane. You'll notice some similarities. Almost everything that's designed to be very aerodynamic or hydrodynamic, if it's going through a fluid, has these kind of rounded curves that gets a little bit more bulbous or a little bigger towards the middle and then skinnier towards the back. In the front, kind of like a plane, it's got this nose, and then it gets kind of bulbous here, kind of big and roundish. And then towards the back, it kind of tapers off to a small point. And all of that is for very good reasons. If we look at, let's look at some cars too that are designed to go very fast. Fastest production car on Earth today, I believe, is the Koenigsegg. Interesting car company. These cars are all made by hand. And you'll notice that they have this very aerodynamic feel to them. This kind of starts off at a point and then gets bulbous and then ends kind of at a point here. You can see that. And even here you can see that it comes even along the bottom nice and flat, but then it comes up at a point here. Very important reason for that. The coolest thing about the Koenigsegg is the way the doors open. They turn up, they come out and then they turn up. Makes them easier to park in a parking lot. Anyway, I think they've hit 310 miles an hour in this car. Can you believe that? 300 miles an hour. They're almost going the speed of sound in a car that's street legal. It's crazy. All right. So, why? Well, so here are some drag coefficients. So, drag coefficient. Now, the reason there are different drag coefficients comes from this turbulence factor. And it's dependent on a couple of different things. In air, here are some drag coefficients in air. I think, yeah. All this stuff is in air. And so it's dependent on the air, but it's also dependent on the shape. But why is it dependent on the shape? When you put something inside, like this is a wind tunnel, and wind tunnels are designed to show when you have turbulence. So let's do a wind tunnel picture. When you put a car in a wind tunnel, what you want to do is you put these little smoke things over the top of it. And as the smoke goes over the top of it, you see that it makes these lines over the top. Anywhere these lines get a little bit bumpy, that's where you have turbulence. There's really important things with cars. First of all, you want air to go underneath the car and have very little turbulence. You want air to go over the car and have very little turbulence out the back. And you don't want any of these lines to get too close together and cross. If they cross, then you'll have huge amounts of turbulence. So, see, this one's not a very good car. You can see the turbulence right here at the front of the car. That's going to cause essentially the car to lift up a little bit. It creates high pressure. You have high pressure zones where you get turbulence, and that causes issues for the car. Here, you don't have that in the front. It's not nearly as much anyway, and on the back, it's much less as well. You want to try to limit that as much as you possibly can. They actually do, so this one's a computer model of that, where they have this wind that comes in and goes under here, and how it comes out on the sides. They do models of this all the time. And it's designed to do this. It's designed to go in and come around the car and go back. All this stuff is specifically designed this way. It's kind of amazing how much they put into this. It's quite important. So shape matters, the fluid matters. Determines a lot about what a car is going to do. So anyway, in some cases they actually try to create turbulence. So in some cases they put a little wing on the back here that will create more turbulence here, and that creates a higher pressure down here which pushes the back wheels down to the ground, and that helps keep control on the car. And sometimes it's a Volkswagen and it's not designed well at all and it has all kinds of turbulence back there. Not designed for turbulence issues. Anyway. So drag forces, the shape matters, the fluid matters, the speed matters, lots of things matter. In swimming, they created these swimsuits back in 2000 something, 2008 looks like. And these swimsuits were designed to reduce the turbulence and reduce the drag in the water. And every single world record was broken that year. So they decided to make them illegal. It was just too much of an advantage. And it mostly came down to money. The swimmers who could afford the best suits were getting much better designs, and so here you have these are the American swimmers of that Olympics. One of the swimmers I coached used to actually swim with Michael Phelps. I don't know if he still does. I don't know if he still swims professionally. His wife does. His wife just swam in the last Olympics and got 2 gold medals or 3 gold medals. Not sure if Andy still does. Anyway, so how does drag force fit into the equation? It's similar to friction. It's part of the net force in the direction that you're moving. So if you're moving this way, your drag force will be this way. And if you're moving this way, your drag force will be this way. And so it becomes part of a net force, and it is usually subtracted off in most situations. It really depends on how you set up your equation. If you're moving this way, and this is your negative direction, then of course this one will be positive. Your drag force will be positive. But most people set up their problems so that the direction they're going is the positive direction. Whatever works. Here they have a situation where the drag on an object is making them stop, and that happens all the time with things falling through the air or things falling through the water. It doesn't make them stop; it makes their acceleration go to zero. But as you're a skydiver and you jump out of a plane, you go faster and faster and faster, but then eventually you slow down, or you not slow down, but your acceleration decreases until you've reached the fastest speed you're going to reach. And that's called the terminal velocity. You can't go any faster because what's happened at that point is that gravity is pulling you down with 9.8, and the drag force is pushing you up with 9.8 meters per second of acceleration. So the acceleration that the essentially the force of gravity down on your body equals the drag force up on your body, and so you stop accelerating and you stay at that constant speed. If you're not wearing any kind of special suit and you've got your arms and legs spread out so that you're covering the maximum amount of area, making a lot of turbulence, that's usually about 100 and something miles per hour. And they actually solve for that here because in that case, your weight minus the drag force equals your mass times acceleration. Acceleration equals 0. That means that your weight equals the drag force, and then you can set it up so that the weight equals the drag force and solve for the v in the equation right there. So they go ahead and solve for that, and it turns out that it's about 180, 200 miles an hour, something like that. 350 kilometers per hour. It's about 200 miles an hour. Which, by the way, is really fast. You ever heard of wingsuit diving before? Wingsuit flying? Where these guys put on these special suits and jump off mountains and stuff. Yeah. One of the best wingsuit divers in the world died last year. He and his friend died jumping in Yosemite, which it's illegal to jump in. Because when you're going that fast, you make one mistake, you're dead. So here they ask you to find the terminal velocity. That's easy. It's just plugging the right numbers, right? If a skydiver is falling through the air, the only thing that you really have to look up is the density. You have to look up two things: density of air and the coefficient of the skydiver, and that's up here in skydiver going horizontally, right there, 1. So they're using 1, I'm sure, for that. Yep, there's their 1. Then you can kind of estimate. An average human has a area, cross-sectional area of about 0.7 meters, and they estimate that by saying 2 meters tall, which is that's actually pretty tall. That's like 6'5" or 6'4" or something like that. But let's say they're 2 meters tall and they're about 1/3 of a meter wide. That's reasonable. So that's a pretty good approximation. And then here is one: if your object is very, very small, or it's in something very, very thick. Okay, very, very gloopy, like liquids. Most liquids qualify in this. Then we use what's called Stokes' law. And Stokes' law combined with the drag force law. In the math, both of them are combined to get you the real answer. But for faster moving objects, this is a very small force, and compared to the other one. And for slower moving objects, this one is actually the much bigger force. So that's why they split it into two different things. This one's called Stokes' law, and you can see you have a 6 and a pi in here, and then we have a radius, and then we have this funny looking n, which we call a mu, and then we have the velocity in, so this is dependent directly on the velocity. And the r is the radius of the object, the mu is the viscosity of the fluid, which is kind of like the gloopiness or stickiness of the fluid. Like oil has a higher viscosity than water. And lots of things in nature and in inventions of mankind that take advantage of these ideas. Geese fly in formation, as do fish swim in formation, to lower the drag. And cyclists and road racers and motorcyclists and everything else all do very similar things. They essentially reduce the drag on themselves by traveling together. So remember, the car has this point. The car had the pointy tip, and then it kind of tapered off to a point at the end. In the case of geese flying, it's very similar, except that they have kind of two tips. They start with one tip and then they have two tips out here. And for every goose that's flying out here, it's much easier for them to fly in this formation. And it's never the same geese in the lead. The geese, the one goose that's right up here at the front has the hardest job, although their job is easier also. It's easier to have a goose flying on each wing than it is to not, because of turbulence. When there's a goose flying behind them, it actually reduces the turbulence because that flow can be laminar. That if they were in a wind tunnel, you'd see nice lines of flow behind that geese and that goose that's in the front, and they wouldn't have to fight that turbulence. They wouldn't have to fight that high pressure region behind them. So they have it easiest, or they have it hardest, but it's still easier than flying by themselves. And it's always changing. And that's on purpose as well. That's something that has evolved over time. That this shape of this flying V formation thing is always changing. So one goose isn't always doing the hard work, right? Same with fish. Watching fish do this is pretty amazing. Same with bats. Bats do a very similar thing. It's just about anything, any animal that travels at high speeds through air or fluid. They try to take advantage of this to lower that drag force or the. I mean, it happens with everything. It's not related. It's not. What am I trying to say? It's everywhere. That's all I'm saying. So. Now, this is the last part of this chapter, and it's kind of weird because it doesn't really connect with anything else in this chapter. It's like this chapter, they just said, well, we have these three other things we want to talk about. We'll throw them in this chapter. This is called Stress and Strain. Anyway, this has to do with how objects made of like solid materials behave kind of like springs. So we're kind of taking a big jump to something completely new here. So this is all due to what we call Hooke's law and deformation. So Hooke was this scientist who lived back about the same time as Isaac Newton, actually, a little bit. Let's see, a little bit before Isaac Newton, I want to say, maybe 100 years. He was one of the original members of the first scientific society, the Royal Society, and was a member in that society alongside one of my great grandfathers, Philip Packer, Esquire. Here is my great ancestor, Philip Packer, Esquire. This is his son, Philip Packer, Esquire. All these portraits are online now because they sold their castle. Somebody bought their castle and sold everything in the castle that had been there for hundreds of years. But anyway, here's the castle. Not so much a castle as has a moat around it though, which is kind of cool. Anyway, they were all in this society, the Royal Society of London, which was the first scientific society, and they were just trying to figure things out in science all the time. And one of the things that this Hooke guy figured out, how do I get away from this? Hooke studied materials. He studied how materials bend and how they spring back after you bend them, if they spring back, and how strong materials were. And that was really important to his work because he was an architect. He actually designed and built that little house with the moat around it and everything. And he did a lot of other buildings in England as well, and bridges and other stuff like that. He was kind of the modern equivalent of a civil engineer, you could say. Hooke came up with this law: force equals K delta L. And what this is that if you have a force on an object that might stretch it, it would stretch it by a certain amount depending on the material, and that's what the K is. The K is this. The K is a proportionality constant depending on the material, and the delta L is how much it stretches. And then if you solve that for delta L, you get this force divided by that constant thing there. And one of the things that he knew is that this only works to a certain point. If you stretch something so much, you'll actually stretch it out. So this is where it starts to stretch out, and if you stretch it out too much, it will stay permanently stretched out. That's happening down here. So the more you pull on something, the more it gets close to just being stretched out forever for good. But here is an illustration of what might happen in this situation. You have three different materials that are not just made of different things, but they're also made differently in size and shape and everything. So they say these two first rods are made of copper or something, and it looks like no, they're doing nylon. So these are plastic. Two strings made of plastic, one thin string and one thick string. So different sizes, shapes-ish. And then they have a piece of steel here, and they add masses to them and see how much they stretch. These would be like guitar strings. The thin one actually stretches more than the thick one when it's the same material. If you have a thicker material, it turns out that it stretches less. If it's the same, if it's thicker sample of the same material. And then a steel stretches much less than nylon. In fact, this is a gross exaggeration. Steel stretches hardly at all, not at all, especially over short distances. So anyway, in any case, to measure this thing, so this thing called K, which is called the elastic constant, or the sometimes called the spring constant, this K, tells you how much something will stretch. The bigger it is, the bigger this K is, the more it stretches under a certain amount of force. So how do you measure that? Well, you start stretching materials, right? And you see how much force it requires to stretch them, and then you plug into that equation and solve for it. So how do we start to decide how far something is going to stretch? It turns out that the length something stretches is dependent on something quite related to the material, called Young's modulus of the material. So this is the Y here is Young's modulus. And then if you have the force divided by the area, that's the pressure on the material. So if you look down the direction that you're stretching in, and you have a big piece of material, you take that area, that's the area. If you have a smaller piece of material, of course it gets to be a smaller area, so that's the area there. And L0 is the original length. This equation defines, this equation actually predicts how much something will stretch if you know the Young's modulus and the cross-sectional area and how much force is the original length. So the original length actually matters. If you have a longer piece of the material and you try to stretch it, it will actually stretch more than a short piece of material. And all these Young's modulus they've all been tested and determined. Aluminum has a Young's modulus of 70 times 10 to the 9 newtons per meter squared. In other words, it takes 70 billion newtons per square meter of aluminum to stretch it 1 meter. It's kind of crazy. So that's very difficult to stretch. Bone, 16 billion. Bone stretches really easily compared to aluminum. And this is one of the reasons that they use titanium that they started using titanium, and then now they use carbon fiber in artificial limbs, because originally they used aluminum. Aluminum just doesn't stretch, so it felt really weird to the people, because when you walk and you move, your bones stretch and compress. They bend and they stretch and they do all these weird things, and that helps to ease the the jarring effect on your body as you walk. But if you had a like a leg made of aluminum, you'd get a lot of jarring. It would hurt your knee, and it would feel really stiff. So they started using other materials. Titanium is a material that's almost as light as aluminum, but very, very springy. It stretches a lot. In fact, my glasses are made of titanium in the nose piece right there. So they do that, right? It's just, it's a beautiful thing because I break glasses all the time. Every time I've had glasses that don't have that titanium, they break. Some glasses you can like tie in knots because the whole thing's made of titanium. Mine's just the nose piece. So other materials, brick, brick actually, it actually bends and stretches as much as bone. That surprises a lot of people. And here, bone is different in tension than compression. Tension is when you're stretching it. Compression is when you're squishing it. Hardwood's about the same, and that's why they use hardwood floors in gymnasiums. So in a gymnasium, when you're jumping on hardwood, you want it to give, you want it to stretch about as much as your body does, so that it's comfortable to jump off and land on. Cast iron doesn't like to bend at all. So this equation here is Young's equation, or Young's modulus equation. And you use it to do problems like this. Like in this one, we have a cable that's stretched for gondolas to go on, and it goes 3,000 meters, and that's like 2 miles. 2 miles. So 2 miles of cable, and it's actually going to stretch. How does it stretch? It stretches because of the weight of the cable, right? The weight of the cable exerts this force on it. In this case, they've designed it so it can withstand this much tension, 3 times 10 to the 6. So the maximum stretch that it's going to be is going to depend on this amount of force on it. So in that case, they put that number in for the force, 3 times 10 to the 6. They calculate their area by using this diameter to calculate the area of a circle, and that's their area. And then they use the Young's modulus for steel, and then they put in pi and the other numbers and throw it all in there, and they get 18 meters of stretch. You say, wait a second, steel's not supposed to stretch much. Well, 18 meters isn't much when it's 3,000 meters to begin with, right? 18 meters is less than 2% of that. So less than 1%. Same thing when you stand on your leg, your bone is going to shorten. The amount of force that you put on your leg is your weight, or half your weight if you're only doing it on one leg, I guess. So 607 newtons of force on your femur, right? And if the cross-sectional area is pi r squared here that they calculate, and they have the area. And if you plug all that into this equation to calculate how much your bone changes length, it's 2 times 10 to the minus 5 meters, it turns out. Which happens to be it's definitely stretching more than the steel cable did in the previous question. So that's Young's modulus, and that's how you use it. You need to know cross-sectional material, you need to know the Young's modulus, you need to know the length, the original length, and then you can calculate the change in length if you have the force. But you can also do other things, like they rearrange it this way, where force is equal to y times a times delta L over L, and this is called the strain. This delta L over L is called the strain. And this force here would be the amount of force you apply, and then y times a over L naught comes out as what we call the spring constant. So that's where the spring constant comes from. It comes from Young's modulus area and the original length of the spring. Now, why do we do all this stuff? Well, it's important stuff. If you're going into medicine, you'll learn about these forces. These are the kinds of forces that break bones and other stuff like this. There's another version of this bending a material, but in this case it's not stretching it or compressing it, it's actually malforming it. So in the case of like a bookcase or a book, instead of trying to stretch the book this way or compress the book this way, what if I push on it this way and make it kind of change its shape sideways? So I'm pressing the top this way and I'm pulling the bottom this way, and it makes the book a different shape from the side, right? And that's what they're doing here with the bookcase. If you push on the top of a really weak bookcase, you know that it will like change its shape because it can't hold itself together. And this is what we call a shear deformation. And this actually is really, really responsible for a lot of broken bones. The shear deformation happens a lot when you stop really quick and you plant your foot. And when you plant your foot, the ground pushes on your foot this way, and your knee goes that way, and your bone gets broken. Right? So shear deformation, force on the top and the force on the bottom, those two forces are equal, and then it changes the area shape here. And it moves the top some distance, little x. It moves one end of it some distance, little x, and there's a distance between the top and the bottom. They call that L naught. And it looks like a very similar equation to before. It still has the force over the area, has the 1 over y, but now it's called 1 over s. Still has the original length, has a delta x. But in this case, we're not calculating how much longer it got or how much shorter it got. We're calculating how much it shifted. Yeah, but it's still the same numbers. The only thing that's different is it uses a 1 over s. And s is called the shear modulus, and every material has a shear modulus as well. And this tells you how strong something is in that direction, in the shearing direction. Quite important for people building buildings and making things that need to be strong in certain ways. So here they have a shearing effect on a nail. You have this nail put in the wall and it's holding a picture frame. The wall is holding the nail up this way, and the picture frame is pulling the nail down this way, so the nail gets this little deflection or this little movement, delta x of 1.8 microns, 1.8 micrometers, and it has this distance between the wall force and the picture hanging on it force of 5 millimeters, so that's your L naught. Right? It has the forces of the weight of the picture, essentially, as your W here. And you plug all those equations, all those numbers into your equation. Your delta x, that's this little deflection, that's how much it moved. Your L naught, that's the distance between the two forces perpendicularly. And then your A, your cross-sectional area. In this case, the cross-sectional area is going to be the area of this nail. So the width of the nail is 1.5 millimeters. You take half that, square it, multiply by pi, you'll get the area, cross-sectional area. And then you plug all those things in here with the shear modulus for steel, because the nail is made of steel, and you get a number of 51 newtons of force required to do that. And then the last one is kind of like the first one, where you're stretching or squishing something, but not just in one line. You're doing it from all sides. So if you drop a balloon, if you drop a balloon full of water into the ocean, for example, most water balloons have a little bit of air in them after you tie them, so that water balloon, it'll sink down a little bit, but then it might float up to the top. As it sinks down a little bit, what happens is the pressure from the seawater all around it will push on it from all sides and squeeze it down a little bit. Okay? Or let's say you have a submarine going under the water. As the submarine goes under the water deeper and deeper and deeper, the pressure of all that water on top of it squeezes the submarine. And you can hear that on a submarine. It's one of the things that freaks submariners out quite a bit, is it actually creaks. The submarine is designed to do this. It's designed to get smaller, but as it gets smaller, it creaks a little bit. And they've tried to get rid of that creaking, not only for the sailors' sakes, but also to make their submarines more quiet. But it just happens. It's the way it is. That's one of the ways that you can track submarines, using sonar is by looking for this creaking. When they go down, when they come up, there's going to be this creaking and popping noises as the hull stretches and compresses. And this happens because of forces on all sides. But it's still the same kind of an equation. Instead of a change in length or something, this one's going to be a change in volume because it's going to either squish it or it's going to get bigger. Instead of 1 over y or 1 over s, it's 1 over b, which is called the bulk modulus. And then there's an original volume V0, and then there's also going to be this A here, and there's still the force on the A, but the force and the A are going to be combined into one thing, force over A, which is pressure. So this is the pressure, force over A. So here's here's an example where we're going to calculate the decrease in volume for seawater if you go down 5 kilometers. And they're going to say the force per unit area, which is the pressure, is going to be 5 times 10 to the 7 meters. So this number here, 5.0, gets put into this equation for F over A. It's like you take this whole fraction and pull it out and put in that number. Once you've done that, then you can plug in the bulk modulus for whatever they're saying, water, I guess. Yeah. Put in the bulk modulus for seawater, and then they want to calculate the percentage change, and that's delta V over V naught, or the change in volume over the original volume, gives you percentage change. And that takes us to the end of chapter 5, I believe. It's a short chapter. And now we have, let's see, let's go back here. Yeah, now we have an exam, huh? You guys excited to do an exam? So we have homework 5. Let's see, exam 5. Yeah, exam 5. Homework 6. 7, 8, 9, 10. I need to read, these aren't labeled properly. That's 12. Let's see here, chapter 8, 9, 10. That's probably pretty good. So, exam chapter 5, due this week on Friday. You can either you can take it at the Success Center here on campus if you like, but the Success Center is kind of in disarray. So if you don't want to do it there, I totally understand. If you'd like to do it with me in the classroom, we could do that also. If you wanted to do it Wednesday, for example, in class, we could do that. But that would mean we'd have to rush to get chapter 6 done on the next Monday. Or we could start chapter 6 today as well. So that's kind of where we're at. Usually, but you can also do it, let's see, what else could we do it? Do you guys know what the Success Center is? Or do you know what it is? The Success Center is essentially a tutoring lab and a testing center here on campus. But they're doing construction. Let's go on a field trip. I'll show you where it is. We'll be right back, everybody who's watching this later. After these messages. We're back. Okay, so moral of the story, make an appointment to take your test before the exam. Make sure that you give yourself enough time. Let's take a look at the time constraints on the exam really quick. So I give 150 minutes, 2.5 hours. And let's see, what questions do we have here? So there are 14 questions on the exam. All of these questions that are on the exam are questions that you've seen before on previous homework assignments. So it won't be the first time you've seen them. And I try to give a nice mixture of questions from different chapters and also different levels of difficulty. I try to give, a few easy questions, a fair amount of kind of medium questions, and then maybe one or two of the little more difficult questions. But usually, if it's one of the really difficult ones, those don't usually show up on the test because it just takes too much time usually. But I try to give a nice mixture of questions, and frankly, most students are fairly pleased with themselves by the time they get done with their first test, and just because they've seen the questions before, it's not a real big surprise. So people are always asking me, what do I do to prepare? Well, you go and you look at your homework, right? You make sure that you can do each one of the homework problems and you remember how to do those. Make sure that you know where things are in the book so that you can find them easily. If you are having trouble finding things in the book on the computer, then print off the things that you think you need to remember in the book. And if you print them off, if they're on the book on the computer, you're more than welcome to make notes in the book on the computer, doing that within your PDF reader or whatever. But if you print it off, you're more than welcome to make notes in your printed off version of the book. However, just pages of notes by themselves are not allowed on the test. So you can have the book with written notes in it. And again, like I said, the reason I do that is because I want people to read the book. I want people to make all the effort they can to understand what's written in the book the best they can. Okay, so that takes us through our first section of the class. We're a third of the way done. How about that? Well, a little bit less than a third, but the next exam that we'll have will take us through chapters 6 through 10, and then the last exam, of course, will be the final, which takes us actually through chapter 17. I need to put on the new homework assignments into this class. But anyway. Anybody have any other questions concerning the exam or any of the procedures? Is anybody interested in taking the test in class and essentially sacrificing class time for that? If all three of you want to do that, we can do it. If you don't, all three of you want to do that, then we can't. Nobody's really that interested.
I think I can work Friday all day.
Can you do the test Thursday?
I'm working Thursday too.
You working Thursday? Well, how do you work? Do you work Monday, Tuesday, Wednesday in the mornings just before you come to class?
6 to 12, 6 to 12 Monday, Tuesday, Wednesday, and then 6 to 5 Thursday, Friday.
So your options are essentially to take it before class, essentially on Wednesday, or to convince these two to do it in class on Wednesday.
I can come before.
Yeah, just make an appointment with them before class. You can go take it before class on Wednesday. That'd be good. And if you want to take it, if it absolutely needs to be done, we can do it after 5 o'clock. But I would just be your proctor. We'd have to set up a time to do it at another time, and that's totally doable. Um, Set up either me or Patrick to be your proctor, and then come and take it in. All right. Any other questions or concerns? Good. Okay, for those of you watching this video later, if you have any questions or concerns, please contact me and we will address those concerns as well as we possibly can. So that takes us to the end of our first section of this class. It is now nearly 5 o'clock. Does anybody have any homework questions from chapter 5 that are beyond the ones that I answered in the emails? Any let's see. Yeah, I guess any homework questions? Did everybody get all their chapter 4 questions answered before it was turned in? Anybody have any other questions? If you did, please, let's get those questions in. We want to get all the questions in before the exam so we can answer them and help you to understand them before the exam. If there are no more questions for chapters 1 through 5, I'm a little bit hesitant to start chapter 6 too early because I know that you guys will be finishing up chapter 5 homework and then studying for chapter 1 through 5 exam. Right now, chapter 5 homework is due tomorrow. Is that going to be okay for everybody? Does anybody need more time, you think? Should that be put on to Wednesday? We'll put that on to Wednesday and we'll start chapter 6 on Wednesday. I'm going to talk a little bit about chapter 6 just to give you an introduction today. But let's try to get chapter 5 completely done by Wednesday, and then we'll push through that exam by Friday. Once again, as far as due dates go, if we need to move them, we can. We'll try to stick to our schedule as much as possible, but I don't want this to be too stressful. I know that summer is tight and busy and crazy and all that stuff. So even if we have to move an exam due date, that's fine too. We just want to try to keep on schedule as much as possible. So let's go ahead and look at chapter 6 really quick. Uniform circular motion and gravitation. This is another one of these times when we're going to take a little bit of a departure into some new stuff. In this chapter, we're going to look at now we're going to take our first look at rotational motion. And in rotational motion, we're going to introduce a new type of coordinate system, kind of. Where instead of looking at how far you go in X and how far you go in Y, we're going to look how far you rotate in an angle and how far out you go. Because you can do that, You can do rotation instead of linear motion and get to the same place. Let me show you how. So here is an axis, X and Y. And let's say we want to get to point A, or we want to get to point B, or we want to get to point C. Right? We can do this two different ways. We can go out in steps on the x-axis, and we can go up in steps on the y-axis. And we'll have two numbers that represent where we are, right? We'll have the y number and the x number. And we usually represent that in a coordinate pair. So let's say that C is out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in the x direction, so we put 10 here. And this one is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 in the y direction, so we put 12 right there. And we know that C is at 10, 12, right? And B is at 1, 2, 3, 4, 5, and 1, 2, 3, 4. So B is at 5, comma 4. And A is at 10, comma like 4, 10, 3 maybe, something like that. So those are the coordinates, and that tells us where we are, where those points are. But we could do it another way. We could do this like we were a big sweeping angle, like we have a big pivot irrigator here. So if you have a big pivot irrigator here and you rotate that pivot so that it comes up to this point right here, making this angle of, let's say that's 10 degrees or something like that. It's actually probably more like 20 degrees. And then we measure how far along the pivot we are, which for this one is going to be about 11. So we're about 11 units along this length of this pivot. Then we have two numbers that tell us where we are using a completely different system. And this one is an angle which will, instead of calling this like x or y, we're going to call this theta. And this one is not x or y, it's more like a vector out here, and we're going to call this number r. And then we have a set of vectors, or set of numbers that we call r and theta, which is, in this case, about 11 and 20 degrees. So it's still a two-number system. And we can tell where we are at B. B is, we turn the pivot to this angle here, which is about 50 degrees or so. And you get there to 50, so this one's going to be about 50 degrees. And it looks like it's maybe about half as far, or a little bit less than half as far as this one was. So let's say this one's about 5 and 50. Can't be 5 because it's 5 up. 1, 2, 3. It's actually, no, it's 5 out. It has to be a little bit further than 5. So maybe it's 6 and 50 degrees-ish. Right? So it's about 6 and 50 degrees is this one. And then this one would be, this one's up here at about 60 degrees maybe. And it looks like it's a little bit longer than this other one. So it's probably about 13 or 14. 14 and 60 degrees-ish. And those are all approximations. But it's a completely new system for determining where things are. And it's a system based on rotation instead of linear motion. When things are rotating, when things are spinning, when things are going around and around and around and around and around, this system makes much more sense to use because it's tracking the motion as it's actually happening. Tracking something in X and Y as it's going around and around and around in circles is a real headache. And tracking things in R and theta when they're going in straight lines is a real headache. It's much easier to choose a system that does what your, choose a coordinate system that does what your actual physical system is doing. We call this system the cylindrical system, or sometimes we call it the radial or rotational system, whatever you want. I can't remember. There's another name for it too, but anyway. But it is just this. It's a rotation of things, and we're going to use this in this next chapter. Here's a classic example of something that has rotation going on. There's rotation going on in the engine. There's rotation going on the wheels as it turns corners and goes around and around a track. It's got that kind of circular motion going on. Lots and lots and lots of circular motion. We're going to deal mostly with what we call uniform circular motion, which means that the path is a circle and that the speed is constant. Remember that velocity is not constant when you're going around a circle. Why is the velocity not constant? What is velocity? What's the difference between velocity and speed? Does anybody remember?
Was velocity that was position?
Well, yeah, not position, but direction, right? So velocity is your speed and your direction. It cares about which way you're going. So if I'm going 50 miles an hour north, that's different velocity than 50 miles an hour east or 50 miles an hour south, right? It's a different velocity, but it's the same speed. It's the same speed as 50 miles an hour east, just a different velocity, right? So velocity cares about which direction you're going. Speed doesn't care. So in our uniform circular motion, we're going to have a constant speed around our circle, but not a constant velocity. Why is it not a constant velocity if it's going around a circle? Because what is changing every time you go around? Your direction is changing. When you're going around a circle, you're turning all the time. You're constantly turning. And that's a change in velocity. So the velocity is not constant when you're going around a circle, but the speed can be. So uniform circular motion is going to be a circle with a constant size or a constant radius, and it's going to be a circle that something is going around it at a constant speed. So just like this kind of normal, anyway, kind of like the Earth going around the sun. That's what we're mostly going to deal with in this class because it's something we can deal with. So the first thing we talk about is what is this rotational angle about? So here's, an ancient piece of technology, the CD. You have your change in angle. Usually we're going to measure our change in angle from the x-axis, and we're going to go counterclockwise to measure that change in angle. If we go counterclockwise, that will be a positive angle. If we measure it in clockwise direction, we'll call that a negative angle. So positive angle is counterclockwise. Clockwise is negative angle. If you want to, one of the things that we're going to want to do is we're going to want to equate the amount of angle that we rotate with the amount of distance that we travel along the edge of our circle. And this actually has everything to do with the circumference of a circle formula. The circumference of a circle formula says that you have 2 pi times r equals the circumference, right? In this case, you have r times the angle equals a part of the circumference. Whereas if we use all of our angle, we'll use 2 pi of it, you can think of it as. That is related. And we're going to use angle not in degrees, but we're going to use it in radians. How many of you have used radians to measure degrees before? Well, I'm going to teach you it right now. So how many degrees are there in a circle? 360 degrees in a circle. What is the formula for the circumference of a circle? I just said it a minute ago. What is the total circumference around a circle? How do you calculate it? Using the radius. Circumference equals what? No, that's area. 2 pi r. Right? That's the circumference of a circle. So if I go around the circle once with a radius of r, let's say the radius is 1. If r equals 1, then the circumference is 2 times pi times 1. The circumference of this one is 2 times pi. Right? But the formula in the book that we just looked at says that if I just go a little bit of a distance, if I just go this part of the way around the circle, then this distance, which they call delta S, is actually equal to the amount of angle that you move through times the radius. Notice the similarity. Here we have a circumference. That's the entire circle. This is just part of the circle. And this equals a theta, a change in theta, or how much angle you go through, which is this angle right here, times radius. This right here is an angle. 2 pi is an angle, just like this one is. But this is for the whole circle. So how much of the angle is 2 pi? The whole circle. So in a circle, you have 360 degrees, right? 360 degrees. Why did we choose 360? Because we love the Egyptians and they like that number. It has nothing to do with anything else except the Egyptians like that number. I'm not kidding. But it's not a very good number to use in science because it doesn't fit in this equation. And it doesn't fit in any equation. It just doesn't work with the math. The number that does work is the Greeks' number. The Greeks figured out that if you take the radius of any circle and you multiply it by 6.28, you'll get the circumference of the circle. So there's actually 6.28 somethings of angle, not 360, 6.28. It's an ugly number, but it works. So we call that number, we call half that number pi. 6.28 is 2 pi. And instead of having 360 degrees of angle, we have what we call 2 times pi radians of angle. So every circle has 2.5 radians of angle. Just like that. So we're going to use radians from now on in this class. Well, for the most part. We'll still use angles sometimes. But that means we're going to have to learn how to convert from radians to degrees. So if 360 degrees is equal to 2 pi radians, and don't write it as 2 pi r because we use r too much in this class. If you're gonna make a if you're gonna do a little thing here, a little shortening of it, just call it rad or something. If 360 degrees equals 2 pi radians, that means you can convert from radians to degrees by doing 360 over 2 pi. That'll give you radians to degrees. Or if you want to do degrees to radians, you do 2 pi over 360. Either way. This one's radians to degrees, this one's degrees to radians. So you can make those conversions pretty simply. But in the end, this equation right here, which is also this one right here, will tell you how much of the circle you've traveled on if you've gone through a certain amount of angle. So if you've gone through pi angle, right? You do multiply, if pi is your delta theta, if that's how much angle you've rotated through, then you take pi, which is your delta theta, multiply it by your radius, and that tells you how much distance you've traveled along the edge of the circle. That's going to be quite useful to us as cars go around turns on the edges of circles, as little flies are on wheels and they go around circles. These are the kind of problems we do in physics. But it'll also tell us how many times a wheel will turn while it's rolling down the road, for example. That's quite important when you're designing tires, when you're designing cars in general. In fact, that's exactly how a car knows how fast it's going. Cars know how fast they're going because they know how long the distance is around the wheel, and then they count how many times the wheel goes around and multiply it by the distance around the wheel. Right? That's how speedometers work. So that is this new rotational cylindrical system of coordinates. This coordinate system. This new thing here, this delta theta, is kind of like it's kind of like a delta x. It's kind of like a distance, but instead of a distance, it's a rotation, right? Instead of how far did you go, it's how far did you rotate, right? So delta theta is a new thing for us. And here they have a nice little conversion table where they convert different angles. 30 degrees of angle is equivalent to pi divided by 6 radians. 60 degrees is pi divided by 3, 90 pi over 2, 120 is 2/3 pi, 135 is 3/4 pi, 180 is pi And oftentimes people will memorize the unit circle. This is sometimes helpful for people. Good thing to print off maybe and glue into a book, or to write into a book or copy into a book electronically. But the unit circle essentially shows you a bunch of these angles going around a triangle. Here they show you the degrees and they show you the radians, but here they also even show you what the coordinate would be on a unit circle where the radius is 1. They show you what the coordinates would be of each of these points along the edge of the circle. Kind of useful. So unit circles are quite useful when you're making these conversions back and forth. So if delta theta is kind of like how much we rotate, what if we rotate a certain amount in a certain amount of time? It's going to be kind of like having a rotational velocity, which we call angular velocity. So if something is spinning around and around and around with a certain rotational speed, in other words, its rotation happens in a certain amount of time, then we take that delta theta and divide it by delta time and we define our rotational or angular velocity. So omega tells us how fast we're rotating. Doesn't tell us how fast we're going from point A to point B directly, but it does tell us how fast we're rotating around the circle, right? Delta theta over delta t. So if you go 1 pi radian in 1 second, then your angular velocity is pi radians per second, because this is measured in radians per second. So pi radians per second is like a half circle every second. You're going around half the circle every second. But the speed along the edge of the circle is going to be this distance along here, delta s, divided by the same amount of time. So if you go around half the circle in 1 second, then how much distance does it travel along the edge of the circle? Well, we go back to this equation where we define delta s and delta theta together. If we know how much angle we went through and we know what the radius was, then we can calculate that delta s. Then if we take that delta s and divide it by the time, we can actually calculate the speed, which is what they do here. But here they replace the delta s with r delta theta because that's what the equation says it is. So we can actually create an equation that tells us how far we've gone along the circle, or sorry, how fast we're traveling along the circle, if we know how fast we're rotating. And it actually just ends up being a multiplication by the radius. So if you know the angular velocity, which is how fast you're rotating, and you know the radius of the circle you're rotating on, r, then you just multiply your angular velocity times your radius, and that will give you the velocity or your speed along the edge of the circle, which we call the tangential speed, or the linear speed sometimes we call it, but mostly tangential speed. That turns out to be quite useful for things like cars. So here's the classic example. You have a car that's rolling down the road. That's an old blues song. Rolling down the road. Sorry, great song. Anyway, so as this wheel rolls, it has this angular velocity of, let's see what it has here. We want to calculate the angular velocity. So we have a 3-meter radius car tire. So the radius is 0.3 meters, and it's going 15 meters per second. If it's going 15 meters per second, that means that 15 meters of this tire has rolled along the road every second, right? With a car. If you go 15 meters, your tires will roll along those 15 meters. So if you have 15 meters of tire rolling down the road, then that is your tangential speed or tangential velocity. And that tangential velocity is equal to omega times r. So if we solve the equation, here's the equation, v equals omega, r times omega. If we solve that for omega, which is how much the wheel is rolling, how fast the wheel is rolling, it gives us omega equals v over r. Well, the v they've given us at 15 meters per second, we plug that in. We plug in the radius, which is 0.3 right here, and we get 50 radians per second for the car tires spinning. That's how many angle, how much angle it's going through every second. Well, how many rotations is that? How much did we decide each rotation of a circle was in angle? How much angle is there in radians every circle? How much times pi? 2. It's about 6, right? So if it's about 6 radians per second, then if you have 50 radians per second, that's like 8 or 9 times around per second, right? Because it's 50 and 1 is 6. Take 50 divided by 6, it gives you 8 or 9. Now we know that this car tire is going around about 8 or 9 times per second. Does that seem reasonable? As cars going down the road, could you imagine the wheel going around 10 times in a second? Think to yourself as you're watching the car go by, 1, 2, 3. Yeah, you can think of that. Wheels are going around pretty quick, right? That makes sense. Sure. That is, I think, where we're going to I think we'll leave it at that for now. And we will pick it up again. Well, let's see. What's next, actually? Let's actually do one more, 2 more sections here. We'll do one more section. Okay. All right, so one last section. So now let's imagine that we're in a car going around a turn here. So here is the center of the circle that is the circle that we're turning on. This is just like a turn on a road. But our car, we're coming down this way, and then we decide to turn, and we turn right here, and then we're going this way, right? What direction are we accelerating in? Remember, what is the definition of acceleration? What changes when you accelerate? What's the change? Change in what equals acceleration? Change in position equals velocity, right? Change in position over time equals velocity. Change in velocity over time equals acceleration, right? So we're looking for how is our velocity changing? When we start our turn right here, our velocity is this direction, upward and to the right. That's velocity 1. So we're going to take that off of the circle and put it up here. When we're done with our turn, our velocity is almost completely to the right. It's this way. If you want to know the difference between two vectors, velocity 2 minus velocity 1, you put them tail to tail, and then you draw a vector from the first one to the second one, and that's what they've done here. This change in velocity is pointing this direction. And if you put it back on the circle right between these two, where the change on average is happening, that will be pointing directly towards the center of the circle. Is that the way we're actually accelerating when we turn? When we turn, are we accelerating? When we turn left, are we accelerating to our left? How many of you have ever taken a turn at high speed? Where you can really feel it get like knocked around in the car or something. You done that before? Shame on you. Terrible drivers. I've heard when I went home, I went to California. My dad, before he died, he went on a spending spree because he had a lot of money kicking around. He'd achieved millionaire status and wanted to spend some money. He never spent any money when I was a kid. We were like, I thought we were poor. Turns out we were not poor. He just didn't like spending money. But anyway, I worked for all my own things from age 14 up. I paid for my own life. But anyway, he went out. He always wanted a convertible, so he wanted to buy a Mazda Miata. So we went out to buy a Mazda Miata, and he came back with a BMW M1 instead. You know, the difference between those two cars is that the BMW M1 has an engine the size and weight of the Mazda Miata. It has a huge V8 engine in it, the top speed of 180 miles an hour, or something like this. But when he died, my mom decided she wanted to keep it. She wanted to keep it so she could drive it to church on Sundays. Anyway, so she drives it to church once a week, and whenever I go up there, she tells me to take it out for a ride, take the kids out for a ride, or take my wife out on a date in it, because it's just a fun car to drive in, a convertible sports car. So I took my son, who's 17. You know, he's only been driving a year, 2 years now, and took him out in it and let him drive it. You know, and he's all careful and student driver kind of thing. So I said, okay, get out of the driver's seat. I'll show you how to drive this car. My parents live at the top of these hills, these winding hills. So I took him down through this neighborhood and never even hit the brake as we came down the hills and around the corners. And, you know, we're going like 45 miles an hour around this 90-degree turn, and the car doesn't even budge, it doesn't even squeal. But you could just so feel all those forces. And then we get onto this highway that goes off into the country, and we're at the stoplight under the freeway, and it's just open country. And I just floored it when we got there. Like as soon as the light turns green, I just floored it 0 to 60 in 4 seconds. Just rip it out there. It was fun. Anyway, as you're going around a turn, what do you feel? If you're turning left, what do you feel in the car? Your body does what? Your body kind of tries to go right, doesn't it? And what's going on is actually Newton's first law, okay? Your body wants to keep going straight because that's what it's already doing, right? Newton says things want to keep doing what they're already doing. When the car turns, your body wants to keep going straight. And what's in your way when the car turns? The door. So you hit the door as the door turns in front of you. The car turns in front of you and the door keeps you in the car. Otherwise, if there was no door and your seat was all oiled and you were wearing a bathing suit or something, you go slipping right out of the car and go straight, the car would turn, right? That's what happens when people hit the brakes really hard or turn really hard and roll their car and not wearing their seatbelt. They keep going straight, they go through the windshield out and, skid along the pavement. Not a pleasant experience if they live through the first part of it. Anyway, this is Newton's first law that makes you want to keep going straight, and the car turns in front of you and the door keeps you in the car. What's happening is the door is pushing you into the circle that the car is turning in. It's the same thing with the wheels. As the wheels are rolling in a straight line, they're going this way. When you want to turn, which way do you turn the wheels? If you want to turn left, you turn this way. Your car wants to keep going this way, but guess what? The wheels are pointing the wrong direction now. And there's friction. There's static friction between the wheels and the road that will not let the car go this way unless you're going super fast. Like if you're going super fast and you turn those wheels, your car will just go over the top of the wheels. It will roll over the top of them, right? That's what happens when you roll a car. I've done that before. I don't recommend it. So what you do when you turn the wheels is that friction, which is between the road and the wheels, is actually 90 degrees to the wheels, pointing towards the center of the circle that you're going to turn on. And when you start turning, that acceleration turns with you. It keeps pointing you towards the center until you straighten out those wheels again, and then there's no force. Because once the wheels are pointing forward, the wheels can roll in the direction you want to go. If you turn them sideways, they can't roll that way. They can only roll this way, right? That's what's happening in a car. It's a force towards the center of your circle. So in every situation where you're turning, your change in velocity is towards the center of the turn. So if you're turning left, it's off to your left. The whole time you're turning, that acceleration is off to the left. And that makes your velocity change direction. It doesn't necessarily change your speed. You can go the same speed the whole time around the circle. but it changes the direction of your speed, so it changes your velocity, and so it's an acceleration. This acceleration, which is center pointing, is called centripetal acceleration, which literally means center pointing. Center pointing, centripetal is the Greek version of center seeking, technically, but it points towards the center. That's what we call the centripetal acceleration. Now you can do the math for this. They actually do the math for this geometry right here. And all you really need to remember is this right here. That the centripetal acceleration can be calculated by taking the speed that you're going along the edge of a circle. If you're going at a constant speed, this only works for constant speed and a constant radius, but if you're going at a constant speed around a circle, you can square that speed and divide by the radius of the circle, and that will tell you the centripetal acceleration. That's an important equation. There's another version of it right here. If you know the angular speed, if you know, or the angular velocity, if you know how fast you're rotating around the circle, and you square that and multiply it by r directly, not divide by r, but multiply by r, that will also tell you your centripetal acceleration. So that'll tell you how much you're accelerating, and the more you accelerate around a turn, the more you'll feel like you're being pushed into the door. You're not actually being pushed into the door. Remember, you're just trying to go straight, and the door is pushing you into the circle, right? So the force is actually pushing you back into the circle. Now, this should be obvious to us, but it's not. How many of you have ever played with a ball on a string and just swung it around? For some reason, everybody's done that. Why? It's not like a game anybody plays. But everybody's like swung something around on a, like back in the day, like my dad's day, they would tie a string to a dead cat and like swing it around. That's really weird. Why would they do that? I don't know. It's like this fascination with swinging things. But anyway, how do you keep that thing from flying away? How do you keep your dead cat from flying away and hitting somebody in the face? You hang on to the string. You pull it back towards the center of the circle, right? In fact, if you pull it at just the right time, you can keep it swinging all the time, right? So you can kind of get this motion going. That is centripetal acceleration. The string is creating a force, which coincidentally we call the centripetal force, that pulls you towards the center of the circle. A lot of people talk about the centrifugal force, which pushes you out in towards the car door or whatever. That centrifugal force isn't real. It doesn't exist. It's not a force. It's just the cat is trying to keep going straight, and you pull it back into this circle. And if you let go of the string while it's over here, it will just go in a straight line out this way. If you let go of it while it's in front of you, it'll go in a straight line sideways. If you let go of it while it's on this side going backwards, it'll go backwards. It will go in a straight line if you let go of the string. But if you hang on to that string, it pulls it back into that circle and creates that centripetal force, which creates the centripetal acceleration, which creates the circular motion. Here they're going to compare the centripetal acceleration of a car around a curve. So a car is going around a curve, the radius is 500 meters, the speed of the car is 25 meters per second. You square the speed, divide by the radius. Square the speed, divide by the radius, 1.25 meters per second squared. It's about 1/6 of gravity. You'll notice it, you'll feel it, 1/6 of gravity. Gravity is 9.8. If you've ever been around a turn, I mean, this is at 25 meters per second, which is about 50 miles per hour around a 500 meter turn. 500 meter turn is bigger than most freeway exit turns in Nebraska. There are 500 meter turns in California. I've never seen one in Nebraska. But there are some big ones in California that are that big. And here's my favorite one. You'll love this. This is an intersection between I-80 actually. So I-80 comes down from Sacramento towards San Francisco, but it doesn't go into San Francisco. It goes into Oakland, California, through a bunch of other towns. But it comes in through Oakland on the east side of the bay. And then 580, which is just a short freeway that just goes from the center of California to San Francisco, and it ends there. It's short, maybe 50 miles or so, 50 or 60 mile long freeway. It crosses 80 at this point, but there's another freeway that goes to the other side. Well, Highway 1 it goes to Highway 1 by 880. But there's like 7 freeways that intersect at this one place. And it's called the MacArthur Maze, and it's pretty amazing. There it is right there. So this one is, this is I-80 here. This is 580 here. Those are some 500-meter turns right there. And it's 7 stories tall, this thing. 7 different layers of different highways. Each one of these at least 3 or 4 lanes wide. And these freeways coming in are 8 lanes wide, both sides. That's a serious highway. Gotta love it. I used to go through that a couple of times. A week on my way to rehearsal with the San Francisco Boys Chorus as a kid. Anyway. So anyway, we're here. We got our 500-meter radius curve, right? At 50 miles an hour. But what if you go at 50 miles an hour and you go like your standard turn in a neighborhood is 25 meters or less. Could be 10 meters in a just a standard neighborhood. Let's see how it comes out. So let's do that one. If we go at 50 miles an hour, yeah, that's 25. So it's 25 squared divided by 25, so it's going to be 25, right? It's going to be 25 meters per second squared of rate. So that's going to be 2.5 times gravity. You ever wonder why these race car drivers have to be in good shape? Race car drivers have to be in incredibly good shape because they're going around turns and they have to hang onto a wheel while it's being pulled away from them more than 2.5 times the weight of gravity. So it's like their steering wheel, which, you know, normally a steering wheel doesn't take much to hang on to, but it's like somebody's trying to tear it away at 2.5 times the weight of the steering wheel. Somebody's trying to grab it and tear it away from it. They have to be extremely strong. So their whole body has to be fairly strong. So, anyway. All right. Here's an ultra centrifuge. In a centrifuge, they have this spinning apparatus that you put little test tubes on. And you ever done this in how many of you have taken chemistry before? Done this? Have you used a centrifuge where you spin it and it separates the precipitate from the solution, or whatever? So that's what that does, really. But my favorite centrifuge is the one at NASA. So at NASA, they have centrifuges for people. They put people on their centrifuges, and they're astronauts that they put on these to test them to see how much force they can handle. And the best one are these ones where you actually sit in this little pod. You sit inside of this thing here. Let's see if they have a good picture of what it looks like on the inside. But you sit inside of this pod, and then they spin you around and around and around. And this is actually where my dad worked, right here. I think my brother went in this one when he was a kid. I was too young to go on it. They can get these things going so fast that you feel 10, 20, 30 times gravity. And this right here is probably about 10 times gravity. It doesn't seem like it's going fast, but it's going fast. And it can go a lot faster than that. Oh, here's a great one.
This is the Royal Air Force Training Centrifuge.
So he's going to get in it and do this. So at 1G...
Spin down. Oh, here we go. Even though the acceleration is high, the jerk here is relatively low, about 1G per second.
He's at 2
Jerk is the difference between a
Gs.
rocket to space, which might take a couple of minutes to reach peak acceleration, and a fighter jet.
Can you hear how his voice is getting really strange? It actually affects your body so that you can't speak, because to speak you have to squeeze air out of your lungs. Well, this is actually going to hold the air into your lungs. So you have to really work hard just to breathe.
where manoeuvres might change the G-force acting on you in a fraction of a second. And it can go further than that. You can measure the rate of change of jerk.
The straining manoeuvre in the chest, and when you lose blood pressure to your head, you could even lose consciousness, and we term that G-induced loss of consciousness or G-lock.
Almost passed out there.
Blimey! I lost everything there. Wow!
3.6
G-lock in
Gs.
itself is not dangerous, but the real
And we're going to go
9
through the
G.
checklist, Laszlo. You know where to find the emergency escapes. So, but I recommend that you... Nice job. 15 seconds.
Yep.
It's like pulling his face down.
20.
Yep.
So what he's doing here is he's trying to flex his legs and flex his
And hold your
abdomen
legs strained all the
to
way
keep
down.
the air coming up to his brain to keep him from passing out. And the blood. He's trying to keep the blood in his brain.
Okay, that was 9 Gs for 30 seconds.
Yeah.
Any problems?
No?
No?
Anyway, so gotta love it. Do anything for science, right? So here they calculate how much the acceleration is in this ultracentrifuge if it has a 7.5 centimeter radius and it's spinning at 7.5 times 10 to the fourth revolutions per minute. Now revolutions per minute is not radians per second. We have to make a conversion here. Remember that there's 2 pi radians every revolution. So we have to use that as our first, we have to convert revolutions into radians. For every revolution there's 2 pi radians, so we do 2 pi radians per revolution. And then there's 1 minute for every 60 seconds, so we have to do that conversion. So 7.5 times 10 to the 4 revolutions per minute, which is 75,000 revolutions per minute, is 7,854 radians per second. That's the actual omega or angular velocity. To get the centripetal acceleration, we do r times angular velocity squared. The radius is the 7.5 centimeters, which is 0.075 meters, multiplied by our omega, and we get 4.63 times 10 to the 6 meters per second squared. 4.6 million meters per second of centripetal acceleration. That's a lot of acceleration. So that happens to be 400,000 G, 472,000 Gs. A human being could not survive that. But a beaker full of, precipitate and solution can handle it just fine. No problem. I think that's as far as we'll go today. That's just kind of gives an introduction to rotational stuff a little bit. We'll cover some more stuff next time. We'll do a little review of this next time as well. But if you get done with your homework 5 early, this will definitely give you a little bit of a head start on homework 6, so you can start on that. Any other questions about the test or anything else before we break for the day? Tomorrow we'll have a lab. Wednesday we'll come back and do some more chapter 6. Answer any last minute questions you have for the exam, unless you've already taken the exam. And you can use a calculator on the exam, scratch paper, your book, and any notes that you have taken in your book. You can use your little plastic coated cheat sheet if you want to use that. And you can use your own computer if you want. Just be aware that the testing center will check up on your computer to make sure that you're not trying to communicate with somebody that's your favorite physicist to help you with the physics problems. Very few students know physicists. Like I'm the only physicist most students will ever meet, so it's not usually a big problem. But anyway, if you don't have any more questions, we can be done for the day. Have a good evening. Enjoy.